So this is the cross-sectional view of a reducing elbow. You can see, so it is used to deflate the water um, at a rate of 14 kg per second. So this is the flow rate. This is the horizontal pipe. It was horizontal and suddenly, just rise 30-degree angle to the upward directions, and it's accelerating like this. So this is the outlet, this is the inlet, and it is discharging the water into the atmosphere through this outlet. So we know the cross-sectional area of the elbow, like this is for the inlet, 7 centimeter square. This is for the outlet. It is the center line, so you can see this elevation difference from the center line to center line. This is 30 centimeter. So this is the center line for this reducing elbow, like the outlet. And we know the from the questions, we know the weight of the elbow, it is negligible, so we are neglecting that. So now the question is, calculate the gas pressure at the center of the inlet, let's say here, and the anchoring force needed to hold the elbow in place. So this is the problem, and we need to just solve the question. So initially we'll write down some assumptions. So the assumptions here, it is this is a steady flow processes, okay? So steady and frictionless, okay? Steady and frictionless flow. Yeah, steady and frictionless flow. Right. The water here, it is discharging through the outlets to the atmosphere. So we need to calculate the gas pressure here. So we'll say, okay, we'll assume that the gas pressure here at the outlet is 0, okay? So we said the gas pressure at outlet it is 0. The outlet gas pressure is 0, okay? And the other assumptions here, you will see, we said we'll assume that the flow is turbulent. The flow is turbulent, okay, and fully developed flow. So at both the inlet and the outlet control volume, and we'll assume that the momentum corrections factor beta, it is equal to 1.03. We use some conservative estimations for this, especially for turbulent flow. It varies from 1.01 to 1.04. So here we assume this is 1.03, and at the both inlet and the outlets. So that's all the assumptions. Importantly, we put the beta equal 1.03. It is a turbulent flow, gas pressure at the outlets is 0, and steady and frictionless flow. So the properties here, the material is water, so the water density we know it is 1000 kg meter cube. Right. So here you can see this straight dotted line, that's the control volume. We defined this is inlet 1, inlet as 0.1 and outlet as 0.2. We have some elevation differences, and if, as we said, it is steady flow processes, one inlet, one outlet, so the mass flow coming through the inlet, mass flow coming through the outlets, going through the outlet is the same. So we can say M1 and M2, they are equal. And you see here the flow rate is given in this question is 14, so we can say it is 14 kg per second. So this is the mass flow rate given, right? But we know the mass flow rate, but what is the velocities at the inlet and the outlet? Because the pipe, it's different diameter at the inlet and the outlet. So what will be the we know the area, we know the cross-sectional area. So what is the velocity here? So what we can do, guys, here at point 1, or you can say inlet, we can calculate the velocity by using the formula, mass flow rate formula. We know mass flow rate equal density, cross-sectional area, and the velocity. At it is point 1, we can say, okay, B1 A1 just for inlet. So then B1, it will be the mass flow rate density over area. So the mass flow is 14 kg per second. density is, this is 1000 kg per meter cube. Cross-sectional area, you will see here 113 centimeter square, so we can say it is 0.0113 meter square. So if we cancel out the units, then we have this kg, you can cancel it out. So this meter, you see it is kg over meter cube, so we can cancel it out. We will have just one m, so this m, it will go up, this s, it will go down. So this velocity v1, it will be v1, it is equal 1.24 meter per second. So this is the velocity for inlet. So now what's the outlet velocity? So we'll do here for point 2, or you can say the outlet. Okay, so the same thing we need to do, we just need to use the same formula like the m equal rho av. So I will just write it down, b2 equal m2, right, and rho a2. We already know how it works. So this is 14. I'm not writing the units for this one, but it is 7 centimeter square, so it is 7 into 10 to the 4 minus 4 meter square. So it will be 20 meter per second, and that's, you see, and it is expected that velocity at this outlet section, it will be significantly higher than that. So you can see it's higher. So now we know the Bernoulli equations. As we have some elevations here, we need the gas pressure, so we can get it from the Bernoulli equations. Water, when we're talking about the Bernoulli equations, Bernoulli equation is something like this. The Bernoulli equation, if we say this is point 1 and point 2, so we can write P on rho g, B on square 2g, Z on equal P2 rho g, V2 square 2g, and Z2. We are looking for the gas pressure P on at the midsection of the inlet. I can simplify these equations like this. I can write it down like, let's say, P on rho g minus P2 rho g, this is equal V2 square minus V1 square over 2g plus Z2 minus Z1. Can I write it like this? Yes, we can. If we simplify a bit more, we can write P on P2 equal rho g into V2 square minus V1 square over 2g Z2 minus Z1. That we can also write. Yep, we can write here. So the P2, it is here it is discharging the water to the atmosphere. So can I say this P2, this is actually kind of atmospheric pressure. The gas pressure is at 0, but this is atmospheric pressure. And if this is the absolute pressure, this is atmospheric pressure, so then the pressure, it will be the gas pressure at point 1. Okay, we solved some similar problems earlier. So it will be then rho g V2 square minus V1 square over 2g Z2 minus Z1. We're talking about, this is the point, center line. So if it is our coordinate system, this is x coordinates, this is z coordinates, okay, then it is Z1, okay, and here this is Z2. So what will be the value of the Z1? Definitely, if it is the coordinate system, then Z1 0, isn't it? Z1 is 0, so we can say Z1, it is 0, and the Z2 is given 30 centimeter or 0.3 meter. So Z1 is 0. So I will write down this expression in the next phase, and then we'll try to do the calculations. So what we have got, the P, yep, where it is, okay, I can write it down here. So the P1, that means the gas pressure at P1, it is equal, the density gravity V2 square minus V1 square over 2G plus Z2, because Z1 is 0. So density is 1000. Gravity, I can write down the units. It is kg per meter cube. Gravity 9.8 meter per second square. Velocity V1 we know 20 meter per second square, and V1 1.24 meter per second square over 2 into 9.8 meter per second square plus Z2. Z2 is 0.3. That's in meter, I guess. Yeah. So it was, and now we can convert the units like kilonewton. It is 1000 kg meter per second square. If we simplify this, if we use our calculators, so it will be like 202.2 kilonewton per meter square, or you can say 202.2 kPa. That's the gas pressure. So P1 gas, which is at the center of the inlet sections. So that's the first part of this problem. If you read the questions here, the question was calculate the gas pressure at the center of the inlet, and finally the anchoring force need to hold the elbow in place. So the second part is we need to actually calculate the force that's acting on this elbow. So here we actually need to use the momentum equations for this. So we already know the momentum equations. So this is part B. The momentum equations for a steady flow, we already know. It is just the sum of the wall forces. This is the vector component, and the sum of the momentum at the outlet BmV minus for the inlet BmV. Right. So this is the momentum equations we know. So here in this elbow we have, you see, this is the coordinate systems. I should use red color here. So this is the coordinate system. So we have this, the resultant force F(x), F(z). So that's along the x and the z axis. So we assume that okay, this is the positive x axis, this is the the positive z axis. Right. So we also use the gas pressure for this entire system, control volume. So now the momentum equations, you see, this is some of the forces. Another important thing is, you will see guys here, it makes a 30-degree angles, right? A 30-degree angles with that displacement. So if I draw it like this, it's kind of like this. It makes 30-degree angle. Okay, and what is this? You see, you just look here. So this is actually V2. This is 30-degree angle. So this is V2, the velocity. Now, we all know, I'm not going to explain it anymore, but we all know if the angle is here 30, and if it is the projections, so it will be V2 sine 30. Okay, or sine theta, so I say sine 30. This is V2 cos 30. So that we already know. So this is the, when we're talking about the forces, so here we have the F(x), and also here the gas pressure is acting. Gas pressure acting at this point. So the pressure force, that means we need to multiply the pressure into the cross-sectional area. And now I will just write it down here because it is quite. This is F equals sum of, this is the outlet, sorry, it is beta mass flow rate, the velocity. For inlet, it is beta, the mass flow rate, the velocity. We have two forces here. When we're talking about the x, the momentum equations along the, this is for the entire system. Now we'll talk about, we have two coordinates, x and z. Along the x coordinates, okay, when we'll talk about the x coordinates, for x, what is the force? F R x, this is 1, plus the pressure force acting, the gas pressure, we can say P on gas pressure. When it will be force, if we multiply by the area. But this section, it is section 1 or the point 1 inlet, we can say this is A1. Okay, so yeah, so this is the gas pressure into the area A1. So that's the sum of the all forces. Right, now what is this for the outlet? For the outlet, we will have it is, the beta. We have only one outlet, so we do not need the summation anymore, but we can write it down like beta m dot, as it makes this velocity, it makes an angle v2, it makes angle theta, so it will be v2 sine theta, this is v2 cos theta. So for horizontal on, it will be then v2 cos theta, v2, because this is the x-axis and this is the z-axis. When we will talk about the z-axis, then it will be v sine theta. So this is for outlet. For inlet, this is simple as it is, beta m dot, and instead of v, it is the v1. That's it. So this is along the x-axis. Along the z-axis, what we will have? Z-axis, we have only F R Z. We do not have any more forces acting there. So it is equal, we have only this. So we can say beta m dot v2 sine theta or sine 30. So that's actually the important part, I think. Now you can solve this problem. So this is for x, we use the momentum equations along the x and z axis, and this is for z. Now what you need to do, you need to calculate the values. So we already know, we define the value beta. Beta, we said for inlet, for outlet, this is same 1.03. So you all know all the the variables, all the the values like beta m dot v2 cos theta, everything you know. So if I quickly just write down for x, if I simplify and write a for x, it is then I said beta 1, beta 2, it's equal beta, so I just make a common term, beta m, and v2 cos theta minus v1 and minus the p1, the gas pressure, into the area A1. So beta is 1.03, the mass flow rate is 14 kg per second, v2 20, cos theta is 30, v1 is 1.24, this is let's say meter per second, minus the gas pressure P, it is it was 202.2, so it is 202.00 Newton per meter square. We convert it in Newton per meter square, and the cross sectional area, it was 0 for section on 0.0113 meter square. So that's the values we have. So if we solve the first part, okay, so then it will be 232, and the second part it will be 2285. So we have got it is 2053 Newton. So FRX, it is negative 2053 Newton. So that means if see, we got it is negative results. So that means the directions what we assumed, it is wrong. Our assumption is wrong. So it should be just opposite. It should be reversed. So that means this FRX, it is actually acting negative x-axis, along negative x-axis. Similarly, FRZ equal beta m and sine theta. Okay, v2 sine theta, sorry. So beta is 1.03, m is 14, and v2 equal 20, sine 30. So if we convert the unit, if we can multiply just 1 Newton equal 1 kg meter per second square, so it will be 1.44 Newton. So that's the F or Z, that's the anchoring force is acting along the Z axis. So this is the total force that's required to keep the elbow in place. So the important part was here, we got it as negative, so that means our assumption was wrong and it should work.